Yes, hello students. This is Murugesan, is physics faculty, E for you, NEET JE. So this session we are going to discuss the theory part of CBSE chapter 8 electromagnetic waves, or shortly we can call it as EM waves or EMW. The first concept what we are going to discuss is the concept of displacement current. Important one, concept of displacement current. First of all, we please recall about the Ampere's circuital law. Yes, Ampere's circuital law. What it says means the line integral of B dot dl, that is equal to mu naught times of I enclosed. Mu naught times of what, children? I enclosed. So this is the formula for Ampere's circuital law. Now please consider a capacitor system, a charging capacitor. So for example, case 1 is just see that a capacitor of capacitance C is connected with a power supply. During the charging process, let us consider I be the current is flowing through the circuit, and this current is assumed as to be time varying current. That means with respect to time, the value of current may be differ. So that's why it is called time varying current. Since the one end is connected to positive terminal, therefore this plate will act as a positive plate and this will act as what, children? Negative plate. Yes, this is the current passing through in it. We know that a current carrying conductor produces the magnetic field around it. So let us consider a point P which is at a distance R from the wire. Now I am considering a Amperian loop in the form of a circle of radius R. Then by using this Ampere circuital law, then I can get this. For this small region, we can consider B as to be constant, and the integral dl is nothing but the circumference of this Amperian loop. Therefore, I can write that B into 2 pi r, that is equal to mu naught. The current which is passing through this Amperian loop will be I, because it is entered and it is coming out from this Amperian loop. Therefore, the current is I. So from these results, we can say that the value of B is non-zero value. Value of B is what, children? Non-zero value. But for the same capacitor system, now you please consider case number 2. I am going to change the shape of the Amperian loop. Here it's a simple circle, but now you please consider the same system, same capacitor system. Yes, so the same current I is passing through in it. This is the positive as a plate, and this will be charging as capacitor's negative plate. This is the measuring point as we consider the same position at a distance R from that. But now what I am going to do is I am just going to change the shape of the Amperian loop. Shape of the what, children? Amperian loop. You just consider this is my Amperian loop. Yes. Now you please evaluate this as integral for this closed surface. You can evaluate this integration that we can get. Yes, you just see that, children. So that left side part of the Ampere circuital law is nothing but B into 2 pi r, that is equal to mu naught. But you just consider this Amperian loop. The current I is entering, but no current is coming out from this Amperian loop. Therefore, I can say that the current enclosed by the Amperian loop has to be 0. Therefore, from this we can say that B equal to 0. That means for the same system, for the same measuring points, one case the value of magnetic field is non-zero, but one case the value of magnetic field is 0 by just simply changing the shape of the Amperian loop. Shape of the what, children? Amperian loop. So this type of contradiction arises when we are using Ampere circuital law in the charging capacitor. In order to remove this contradiction, what Maxwell's gave some idea. Some current is exist between the plates of the capacitor during the charging process when the time varying current is passing through the capacitor for the charging process. So we know that as according to Maxwell, what he says, there will be some current. Because why here B has to be 0 means because there is no current. Suppose if you are assuming that some current is coming out from this between the plates of the capacitor, then this term won't be 0, then B also non-zero and same as to be the previous one. So for that reason, Maxwell's assumed that there will be some current between the plates of the capacitor, but we know that there is no actual movement of the charges between the plates. But the thing what is exists between the plates of the capacitor is, obviously we know that yes, electric field only, because we know that the electric field lines are going from positive to yes, negative of the yes, capacitor plates. So this is the electric field exists between the yes, capacitor. But we know that the current what we are sending is a time varying current. With respect to time, the value of current will be changed in that circuit, which results the changing yes, electric field between the plates of the yes, capacitor. But we know that yes, we know that between the two oppositely charged sheets, by the applications of Gauss law, yes, we come to know that the electric field, magnitude of the electric field between the plates of the capacitor is given by E equal to sigma by epsilon naught, or this sigma is nothing but Q by A. We know that type of charge distribution. Since we just see that, as we said, just see that current what we are passing is called time varying current. With respect to time, the value of current is changing. So therefore, the amount of electric field between the plates of the capacitor also change with respect to time. So therefore, I can write this. This has to be, I can rewrite this. So therefore, Q is equal to EA into epsilon naught. We know that the product of E into A, that is electric field into area, is nothing but electric flux pi. Therefore, I can write that pi E, that is electric flux, into what, children? Epsilon naught. But the charging process, during the charging process, the magnitude of the charge is not constant between the plates of the capacitor, since it is varying with respect to time. Therefore, I can differentiate with respect to time. So therefore, dq by dt, that is equal to epsilon naught. Since electric field is changing, even though the capacitor plate area remains constant, the electric field will vary with respect to time. Therefore, the quantity electric flux also will vary with respect to time. Therefore, epsilon naught into, I can write that is what, children? D pi by dt. We know that dq by dt is generally nothing but what, children? Yes, the current is I, the current I, that is a dimension of the current I. So I is equal to what, children? Dq by dt, that is equal to what, children? Epsilon naught d pi by dt. And this term is called as displacement current by the Maxwell. So because the displacement current is exists between the plates of the capacitor. Now you please come to this case. Now according to Maxwell, what he says, some current is exist between the plates of the capacitor. Between the plates of the capacitor, that current direction is shown like this, and that current is called ID, displacement current. Now please apply the Ampere's rule now. Some current is coming out from the Ampere loop. Therefore, the current enclosed by the Ampere loop will not be zero. So therefore, the magnetic field will not be zero. That means the results what we are getting in case 1 and case 2 will be same by considering the the value of the concept of the existence of the displacement current. So in this manner, the the different results by getting different Amperian loop can be overcome by the concept of displacement current. Now please see that, children. So therefore the modified Ampere's circuital law. Modified Ampere's circuital law is generally called what, children? As Ampere's Maxwell's law. So Ampere's Maxwell rule or Maxwell's law. What it says? The same relation only. So line integral B dot dl vector, that is equal to mu naught. This term alone gets changed. I enclosed. This I enclosed means it's sum of the two current IC plus ID, where IC called what, children? Conduction current. Conduction current means due to the flow of electron, there will be actual movement of the electron in the wire. Displacement current means due to the change in electric flux between the plates of the capacitor. Therefore, now this is the modified Ampere's circuital law, or we can say that Ampere's Maxwell's law. So in this case you just see that outside of the capacitor plate, outside of the capacitor, that means you just see the diagram. This is the outside of the capacitor plates. The current what is passing through that is called the conduction current, which is passing through the wire due to the flow of electron. So in this case conduction current is non-zero, which is nothing but dq by dt, but the displacement current is zero because there is no electric field. But between the plates of the capacitor or inside the capacitor, I can say that inside the capacitor, yes, electrons are not flowing from a positive charge plate to negative plate, but the electric field only can exist. That varying electric field results some current between the plates of the capacitor. That is called what, children? Displacement current id. Therefore, yes, inside the capacitor plates we can say that IC equal to 0, but ID, that is equal to epsilon naught d pi e by dt as non-zero value. So whatever may be the case, yes, in order to satisfy the continuity property, so by the continuity property, the magnitude of the origin may be different, but the magnitude of the conduction current and the displacement currents are equal. Magnitude of the conduction current and displacement currents are what, children? Equal, but the origin will be different. Conduction current is due to the flow of electrons, but the displacement current is due to the change in electric flux between the plates of the capacitor. Yes, once the capacitor reaches the steady state, obviously we know that there is no change in electric field, and obviously displacement current will be zero, and there is no flow of current through the capacitor. That is called a steady state, what we are already discussed. Okay, children? Yes. So this is the another important point. So once the system reaches, that means the capacitor reaches the a steady state, that is fully charged means. So at steady state, obviously we know that the capacitor does not conduct the current, or there is no flow of current through the capacitor. Therefore in that case I will be 0. Yes. So yes, these are the information related to Ampere's circuital law and its modification as proposed by Maxwell's. The only thing what we must consider is in order to get the similar results, even though the shape of the Ampere loops are different, Maxwell's assumed that between the plates of the capacitor there will be a displacement current, which will give the result the same as to be the case 1 what we so far discussed. Okay, children? So these things you please keep in mind, and which region which current will be exist, which current is not exist, that alone you please keep in mind. It's very important and a simple concept in EM waves. Yes, children, please kindly note it.